Okay, hello everyone. Today we are going to solve this LeetCode problem, that is median of two sorted arrays, and it's a pretty famous problem. So let's see, and it's a hard question. Okay, it has a difficulty of hard level. Let's see. So you're given two sorted arrays. The first one is nums1, the other one is nums2, and you are also given their sizes, which means that you are sure of how many elements are going to be in the nums1 and nums2, and you want to return the median of these two sorted arrays. So let's first of all understand what do we mean by median. So median has generally two values, okay? So one is n by 2th element if the size of the array is odd, and the other one is n by 2th element plus n by 2th element by 2 if the size is even sized, which means that if you have an array with the size as 1, 2 and 3, so n by 2th element 0, 1, 2, let's say these are the index, and n by 2th element means the size is n is 3 and n by 2 is 3 by 2, and integer division answer will be 1. So first index is the middle element, which means 2 is the middle element. But if we are given an array with size let's say 4, right? In that case the n value is going to be 4, and n by 2 is second 2, and 2 minus 1 is 1, so which means 1th element plus and the n by 2th element, that is second element, over not 1th actually, first element, yeah, and over 2, which means their average, okay? And the first element, uh yeah, so the element which is on the index 1 is 2, and the element which is on the index 2 is 3, so that means 2 plus 3 by 2, which is equal to 5 by 2, and that is 2.5. And by the way, according to this problem, the output has to be in a decimal format. So for that reason, we are either using float or double values. Okay, so it's in 2.5 value. And let's see if we are, yeah. So now I think we are comfortable with the concept of median, and now we can move to another part of the problem, that is to understand how this question, what this question is actually asking us for to in order to calculate the median. So you were given two arrays, okay? So there are two arrays, which is the 1 3 and 1 2. After merging them it will be 1 3 2, and after sorting them it will be 1 2 3. Okay, and this is an odd sized array, so the middle element is going to be the median, which means 2 is the median. Now in this case you are given a merged array, so you're given two arrays and now you want to merge them, 1 2 3 4. Now these arrays are merged, okay, and they are sorted, so we don't need to sort them. I mean, we have to, in in if we are coding, and we have to make sure that the elements are sorted, but in this scenario they're already sorted. And then this is an even sized array, so I'm going to take two middle elements and their average, which means 2 plus 2 plus 3, these two elements divided by 2 is 5 by 2 is equal to 2.5, and that is our answer. Okay, so first of all, so let's build our solution up, and we're going to start from the very basic. So the first approach is to merge the array, then to sort the array, and then find the median. Okay, so merge means that you are given 1 2 4, so you are given this array, the first array, and the second array is 3 5. Okay, after merging them this is going to be 1 2 4 3 5, and after sorting them it's going to be 1 2 3 4 5, and after sorting them you can easily calculate the median. So merging takes order of n plus m times, sorting takes order of n plus m, log of n plus m time, and the median takes constant time, because you only need to check the middle element. You only need to check two things, if it's an odd size or even sized array, and you will get your median in constant time. So the dominant term is this one, which means that the time complexity for this solution is going to be order of n plus m log of n plus m, and the space complexity is we are using this uh, auxiliary space, that is an array to store the merged array, and that is order of n plus m. Okay, so this is the time complexity for the first approach, in which we merge it, then we sort it, and then we find the median. So there's another approach which is a slight optimization over the previous one, and that approach is to merge the elements in a sorted fashion. Because the arrays that are given to us are already sorted, then they are already sorted, so we can take this one condition that is given imposed to us by this question and use it for our for our optimization or solution, and that is to use a two pointer strategy. So you can use a two pointer strategy, and that is to start a pointer on this side and to initiate a pointer. So this is a pointer 1 and this is the pointer 2. Okay, and this is the nums 1, this is the nums 2, and now you have your merged array. Okay, and now you're going to store the element. So whichever element is pointed by the pointer is smaller will be stored in the array, and that element, that pointer element, that pointer which has given us the smaller element will also be incremented, which means that out of this 1 and 3, which one is smaller? 1 is smaller, so we are going to store 1 and we're going to increment 2. We're going to increment the pointer which was pointing on 1, and 2 and 3, who is smaller? 2 is smaller, so we're going to increment this one. 3 and 5, which one is smaller? 3 is smaller, so we're going to increment this one. 4 and 5, which one is smaller? 4 is smaller, so we're going to increment this one. And 5 and 6, which one is smaller? 5 is smaller, so we're going to increment this one. Now when any of these two pointers is now pointing on the out of like the last part of any of their respective array, then we are going to store all other remaining elements pointed by the other pointer. That means this is the other pointer and this is the first pointer that is now pointing on the, that is basically out of bound. So we're going to store all the elements that are pointed by this pointer. Okay, which means from this pointer and so on, but there is only one, so we're going to store only 6. So now we have this array, and this is a sorted array because we have used a two pointer strategy in order to get these arrays. Now this one is also out of one and this one is also out of one, so now we are done with our question. Not exactly. Now we have our merged and sorted array, and now we can easily find the median. And for this array, median will be, because it's an even sized array, so the median will be the average of two middle elements, which means 3 plus 4 by 2, that is 7 by 2, so that is 3.5. Okay, now let's see. So these are the two approaches. Okay, and the time complexity for this one is, I think it's pretty much uh, observant that it's on n plus m, because we are not sorting them manually, we are storing them in such a way that they are already sorted. And the space complexity is still n plus m. Why? Because we are still using an auxiliary array to store the merged elements. Sorry. So yeah, this was the approach where you have so it's like a slight optimization over the previous one. We are using n log n, now we are using only n, although it's still an optimization, but in computer format, or in as a perspective of a machine or a compiler, this is not much of an optimization because log n is still a very small value. So anyways, so we're going to see another approach, and this approach is actually good. This is like okay, so the fourth approach is the best one, and the third one is like a build up for the fourth one. Okay, and that is to apply a linear search, assuming no, based on the assumption that is the middle element, and not checking, actually verifying the assumption. Let's see how we can do that. So let's say you have an array x. Okay, And by the way, I have also taken a lot of, in order to understand this solution, I have taken a lot of help from various resources, either on YouTube or on LeetCode discussion section. So if you want to check them as a, then you can obviously can. So you have X array, and that is X0, X1, X2, X3, X4, X5, and yeah, just X5. Okay. So now you have 6 elements in the X array, and then you have Y array, that is Y0, Y1, Y2, Y3, Y4, Y5, Y6, and Y7. Now you can apply so first of all, the observation why you come up with some solution of linear. So the thought process, my thought process was that if I, if I choose each element, if I say let's pick this element, so let's say that this element is the middle element. Okay. So this is our, so this is my merged array, right? And this is the, middle part. And because it's an even sized arrays, because these so there are 6 elements here, and there are 8 elements here, so total there are 14 elements, right? So this array is of 14 size. Okay, this array is of 14 size. Okay, so if it is of 14 size, then there will be one middle element here and one middle element here, and that is why this partition is there. Okay, now if it is 14, then there will be 7 elements on this side and 7 elements on this side, which means that apart from this medium, apart from this middle element, there will be 6 elements on this side and 6 elements on this side. Okay, and plus one, the middle one. Okay, so this is the one, this is another one. That's it. So now if I say that x is not x0 is one of the middle elements. Okay, x0 is one of the middle elements. Okay, I'll take it. These, so this second half of the merged array is going to have all the elements that are greater than x. Why? Because it's a sorted array, right? So every element that is greater than x will be find here, we can find here easily, and that is x1 to x5. So we store all of the elements. And how many elements are there? 1, 2, 3, 4, and 5. So there are 5 elements. Okay, and we need one more element because we need total 6 remaining elements apart from the median. And the other element is going to be the, okay, so these are, yeah, so other element is going to be the, we are going to take, okay, so we have taken all of the elements from the x array. Now it's pretty much obvious that we need one extra array. And how can we take that? We have to take that element from the y array, right? So our safest bet would be to take the largest element of the y. And why is so? Because we are placing them in the this array, right, in the second half. Because if we take any smaller element and take and place it in the second half, then there is a, then it kinds of contradicts itself, because the remaining y element will then be placed in this one, which means that these elements are greater than this. Let's say we have picked 5 5 and we have placed y0 here, so this is not a sorted array anymore, which is why our safest bet is to take the element which is from the from last or from the end of the y array. So we are going to take y7, and so y7 is now also going to be there. Now you have 5 this and 1 this, so you have 6 extra elements. But this is not done yet. So you have taken x here. Now we need another element, that is y6 as the middle one. Okay, so y6 will be the middle one, which means that you have taken 2 elements from this part y, and 1 element from, and 5 elements from x, right? And this one element belongs to the, so obviously if these elements are taken and put in the second half of the merged array, then the remaining elements of x and y will be put in the first half of the merged array. So x naught will be here, that is the middle element, and all of the remaining elements, that mean y1 to y0 to y5, will be in the first half, right? So let's count the elements: 1 2 3 4 5 6 7. sorry, 1 2 3 4 5 6 and 7. Okay, so there are 7 elements here. 1 2 3 4 5 6 7. Okay, so there are 7 elements here, which means that as of now I have successfully I have successfully, made a partition in x and y, but it's not yet verified. Okay, I have made an assumption. I have made an assumption, successful assumption, but that assumption is not yet verified that if it's a right assumption or not, and we are going to check and look for a condition for that. So out of these, so x naught has to be the smallest one, right, out of the x array. And for this, okay, so let's just think of something so that I can convey you my message or the algorithm solution in the best way possible. Let's say that from x array we have the greatest element. So which one will be the greatest from the x array that is put in the first half? So we only have one element, so x naught will be its own candidate, right? And from the y array, which one will be the maximum so that it can be placed at this side? Because in the first half, the element on the last or the middle, that is the first middle element, will be the greatest, has to be the greatest, right? So from y we will have y5, because this element is greater out of all y, and this x is greater out of all x, although there is only one x. So we need to find the max out of these two, and if we know the max out of these two, then we can say that okay, so max out of these two will be the element that is placed right before the partition, which means that element is the greatest in the first half, right? It makes sense, right? Because if you have 1 2 3 4, right, and this is the partition, then out of this sub array, the first half, the 2 is the greatest, right? 2 is the greatest, and this sub half, 3 is the smallest. So we're going to do the same thing, and the minimum of yeah. So now in this, so this is the part, right? So the y, the elements that are hovered by the y line, so by the white line, are the ones that are stored in the second half of the merged array. So from this, it's pretty much obvious that the element that is the minimum will be stored as the middle element here. So the minimum element will be from y, it can be y naught, and from x it can be x1. And from these two we have to calculate the minimum element. So it will be x1 comma y6, x1 comma y6. So minimum out of these two. Now there's one other condition, 1 2 3 4. Okay, so this is the array. So it's pretty much obvious that 2 will be less than 3, right? 2 will be either less than or equal to 3, which means that the m1, if this is the m1, this is the m2, m1 has to be less than or equal to m2. And if it is not the case, then our assumption was wrong. So if this condition is satisfied on each and every assumption, then we can say that we have found the element that was our, that we have find the middle elements, and now we can easily find our median. So only and only if this condition is satisfied. If this condition is not satisfied, then unfortunately we have to look for the, then our assumption was wrong, so we have to look for this one. And then our array will also change, so we will have these elements in the array, and for this one as well we will have these elements. And so these are second, like the second half, the second half of the merged array. And for the first one, our array will look like something this and something like this. Okay, so now you can check the 2 elements from this side and 5 elements from this side, 7 elements in the first half, less, it's true. And then 4 elements from this side and 3 elements this side, so 7 elements on this side as well, which is also good. And now we have to check for this condition. So in this case, the maximum, so this part, the maximum will be x1, so it will be x1, and the maximum of y4 it will be y4. And for the minimum value of x of another sub of the second subarray will be uh, x2. And for y, the minimum value will be y5. So if this condition is satisfied, then we will say it's right. Otherwise, we are going to move our pointer ahead and we are going to do the same process until and unless this condition is satisfied and we have received our answer. So this was the linear search. Now let's understand the code. So the first thing first, yeah, so the very this is like an another optimization, which is a good thing, because it's solely based on the observation. So if you are given an opportunity to apply a linear search on any of the array, because applying linear search only on the one array is going to give you the partition points of the other array automatically. So why will you bother applying linear search on the largest array, right? On the array which has more elements, you will obvious, it's like an obvious choice that you're going to apply binary search on the on the array which has the least elements, right? That is why we are doing this, that if nums1, so we are assuming that nums1, we are assuming that nums1 is smaller than nums2 or equal to it, okay? But if it is not, then we are going to swap it, because we are using, because this whole algorithm, the second part of the question is of the solution, is based on assumption that n1 is smaller than or equal to n2, okay? That is why we are swapping them. So after swapping them, we can say that nums1 is smaller, okay? So now we can apply linear search on nums1. And one thing to note here is that we have used an equal signs, okay? And I will tell you why we have used the equal sign, okay? So first thing first, so this is, so I'm going to divide it into parts. And yeah, so there are three parts, okay? The first part, and we are going to understand each and every part in depth. So the first part is that we are going to calculate the partition points, which I have told you earlier, these points, okay? So these are the partition points. And if these partition points, and for these partition points, let's say, so for now we are going with this, that I is the partition, which means 0, the 0th element, okay? So we have assumed that the 0 is now the, just a second guys, yeah. So now we made an assumption that 0 is the partition, okay? If 0 is the partition, how to calculate the partition point of y, right? How can we calculate it? Well, let's see. If 0 is the partition, then it means all other elements from this side is now going to be in the second half, right? And all other elements from the y are going to be, and there are some elements that are going to be in the second half as well. So a very easy way to calculate this is that if one element is fixed out of the seven elements, right? Out of seven elements, one element is fixed. How many remaining elements do we have, so that we can take from y? So the formula will be, so 7, let's say, how do we calculate 7? So 14 by 2, that is the 7, and that is the size of our that halves, subarray, minus partition point of this one, that is p of x. So that will be 7, 7 minus of px, that is 0, and that is going to give us the value as 7, which means that the seventh index is our another partition point. But this partition point, which means that if yeah, so it's kind of like saying, yeah, so it's kind of saying that you have this 14 sized array, and now you got your x0, which means this element, okay? And now you have your y7 as well, so y6 will be here, okay? So this is the like an this is like a formula part. And you might say that, can we not just use the y6? Why do we have to use the y7? Well, the reason is that if you have odd elements in that scenario, using y, using the using this formula is also suitable for odd as well as even. Only one slight variation is that you have to pick the element that is before the element that is the partition y, the element that is before the partition y point. So I guess it makes sense. And yeah, there's one other thing. This is the formula that we are calculating because it's an even number. Well, what will be the well, for odd sized array, this formula, the partition y, is not going to be the valid partition. So in order to deal with that, it's very much easy that plus 1 divided by 2. Because it's an integer division, we can take advantage of adding 1, and our answer will be incremented in case of the even, in case of the odd total size array. Okay, so that is why we are using nums1, that is why we are using nums1 size, nums2 size, and plus 1, so that we are good to go for odd size arrays as well. Divide by 2 and partition of this minus. Okay, and now yeah, so now the first part is, I think, complete. Now you can understand why, because if you choose your partition to be, let's say you choose, so at this point you choose your partition to be x0, but it's not the right answers. Now you choose your partition to be x1. So the index is 1, and 7 minus of 1 is going to be 6, which means that p of y is now 6. So this is pointing on, so px is pointing on the first index of x array, and py is pointing on the sixth index of y array. So by this thing you can observe that this is going to be the max left. So this is going to be y5, this is going to be y6, and this element is going to be x1. Okay, and now if you want to check how many elements will be there, so x0 will be there, right? 2 elements, and then all these elements are going to be in the second half, and all these elements are going to be in the second half as well. So this is 4, this is 3, 7 elements, good. This is 2, and this is 5, 7 elements, good. So this formula is working as it should. Okay, now we are going to check, we're going to check for another thing. Yeah, so I think now we are done with partitioning. That is the first part of the question. The second part of the question is calculating the max left and max right. Okay, which means that the element that are on this side and on this side, so we have to calculate them. Now max left x, so this is our left side and this is our right side. Okay, so max left x, which means the element on this side. Okay, so not an element, actually not on this side. So there are two candidates, right? We need to find the elements on, so the element on this side will be max of the, p of x element, or p of y element, right? I mean, not p of y actually. It will be max of an element from x, let's say I, and an element from y, let's say j. Okay, and this element is going to be the minimum of element from x k and the minimum of element from y l, right? Which means that if we say that this is the partition and this is the partition, we are going to take the elements from the left one. We're going to take the elements that are on the previous elements, which means y5 and x0. So these are, so x0 and y5. Okay, so in best way I can say that max of x of p of x minus 1 and y of p of y minus 1. Okay, so this one, and the condition was that, okay, so this place is going to be held by, so let's say this is the number 1, just for better representation, and this is number 2. So this is number 1. Okay, and the number 2 element, the number 2 middle element will be minimum of x of px comma y of py. This element and this element, they have to be minimum, and this element and this element, they have to be the maximum. And if they are, and if the max one, this element is less than equal to the other one, then we will say, okay, so the middle elements are good to go and we can calculate our median. So this is what we are doing. We are taking the partition of x minus 1, right? This is the partition of x, and this is the partition of y, and the one element in the previous element, that is why we are decrementing it by 1. So previous partition of x minus 1, and then partition of y minus 1, so it's going to be our max left x, max left y. So this is our max left x, and this is our max left y. And the min right y and min right x will be partition, the element at partition x and element at partition y. That is why it is px and py, not px minus 1 and py minus 1 in the max left case. So in this is the min right, okay? So this is the min right y, and this is min right x. So after calculating, and yeah, first, and one other thing, so if we have int minimum, so what do we mean by int minimum here is that if our array is at 0, then we obviously know that in the uh, you know let's say your partition point is now pointing on, yeah, so now your partition point is now pointing on this one, so this is px, and if this is px, let's say the 0 is px, so 7 minus 0 is going to be 7, so py is going to be this one, right? What is meant by this? So element on the previous one has to be part of this one, but there is no element. So that is why we are saying int minimum, so that in this case, so the max left x is not other than the minimum value, and it will be ignored, well, not ignored, but any value that is on the max left x will be taken into account, because this is the minimum of the minimum value and this is a max function. So this value will be ignored in a manner. That is why we are taking int min and int min for the max left x and max left y, and for the min right x and min right y we are taking int max and int max, so that the min function can ignore the this value and already start working on other value, or this one, or the value which doesn't have the maximum value. So I think now this second part is also clear. And the third part is pretty simple. If this condition is verified, if this condition is satisfied, that the max of max left x and max left y, you know, this condition, this is the max left x and this is the max left y, and this is the min right x and this is the min right y. So if this condition is satisfied, because any element, this is a and b, so a has to be smaller than or equal to b in a sorted element, right? So if this is satisfied, then we can say that the elements are actually the middle elements, and they are middle elements. So now you can calculate your median, and the median will be calculated as I've stated you earlier in the explanation of the problem, that median has two things. If it is an even size array, like even sized array, then we are going to have the average, like, so this is the average, this is middle one, right? This is middle one and this is middle two, and their average divided by 2 is going to be our answer. Otherwise, if it is not an mid even sized array, then we are going to simply divide, then we are not divide actually, then we're going to simply return the middle element. Okay, and then we will continue with our loop, and uh, I think this return -1 will not work until and unless we don't have any, the m and n are 0. But just for the sake of returning something of for this function, I have given this value. Otherwise, this the whole code is right. You can actually rely on this. If you're not able to understand the linear part, you can again watch the video and try to understand it, because this is like a build up for the optimal solution. And now we're going to, so I think now we are done and we can now discuss the time complexity. So time complexity for this one will be, let's say, so this is a Linear search, and linear search is linear, like order of n or n plus m. Now this is not order of n plus m, this is actually minimum, because we are taking minimum of the array which has the smallest size. So minimum of n comma m. This is the time complexity, and space complexity is order of 1, because we are not using any auxiliary array. So this is like a very optimal approach, but it's not the optimal approach. So now we're going to look at the most optimal approach, and that is the fourth approach. So the fourth approach is, so first we are using linear search. Well, what is the optimal strategy? What is the optimization over linear search? So linear search is used when the array is not sorted. For unsorted array, we can use linear search. But when the array is sorted, we use binary search. So why not? Why should we not take this into our advantage? Why should we not use this to our advantage? That the array is sorted, right? We should use this thing to our advantage, and that means that, so instead of like saying that this is the partition x, and then if this does not work, then this is the partition x. No, we are not going to do that. What we will do is we'll find the middle element. Okay, so this is 6, there are 6 elements, and 6 by 2 is 3. So third one is the middle element. So now px is now pointing on third one, and if px value is this, then according to this formula for the partition y, 7 minus 3 will be 4. So now py is going to point on this one. Py is going to point on this one. Okay, and if py is pointing on this one, then we need to check, then we will be calculating. So this is going to be max left x, this is going to be our max left y, and oh fuck, and this is going to be our min right x, and this is going to be our min right y. Okay, so now the thing is, max out of these two elements, right? The max out of these two elements, that is the x of px minus 1 and x of yp minus 1, which is already given here. This one has to be smaller than or equal to the minimum of px and py. Okay, everything will be similar. We will be calculating partition y just like we have calculated it earlier in the linear search, and the max left x and max left y, min right x and min right y would also be calculated in the similar fashion. The only difference is that if it doesn't work out, right, if this is not the case, well, then there is something which we need to observe then. So if yeah, so what we need to observe is, so if max left x, this element, is greater than the min right y, this element, well, this element has to be smaller and this element has to be greater, but it's not the case. And if it is not the case, then we can say that we are looking for the x values that are too much for us. We cannot use these values, man, these are too much for us, right? So we are going to move our pointer, and we are going to try for the subarray in the x that is on the left side. And to do that in binary search, so this is a low pointer, this is the, so high pointer is actually pointing on the last element, the size of the array. So this is a high pointer. So we, in order to do that, in order to move our binary search and try searching in the left subarray, we move our high pointer. So we are going to move our high pointer to partition x minus 1, which means this one. Okay, so now we will be searching over this array which has smaller values of x. So let me write a condition. So the first condition, well, the first condition is obvious, is I think clear, pretty much clear, that the max of x of p of x minus 1 and y of p of y minus 1 has to be smaller than equal to min of x of px comma y of px, sorry, py. Okay, and the second condition is, if the max of, sorry, if the x of px minus 1 is greater than y of py. So if it is greater than this one, then we will say that move our high pointer to the x of px minus 1. And why do we do that? Because, you know, because we want to now we want to run our binary search on the x elements that are smaller than the previous one, that is xp minus x of px, right? So which is why we will be doing this, yeah. And the third condition is, so if our max left y, okay, which means y of py minus 1 is greater than x of px, is greater than x of px, this one, the minimum one, then let's see it here. If I say that the this x element, this has to be greater than this y element, has to be smaller than this, okay? So this is the relationship between x 3 has to be greater than y3, right? But this is not the case. And when this is not the case, we will say that we are looking for x values that are too smaller. We want to look for the x values that are bigger than the current one. So for that, we will move we move our binary search to the array which has greater values of x, which means the right part, okay? Which means we are going to move it to the right part. And in binary search, if we want to move our binary search to the right subarray, what we will do is we will shift our, so this was, so initially we have high here, so we will and low was here. Now the low will be shift to this part, okay? So now low is pointing on not actually the partition point but the one incremented, okay? So the other one, and that is our code, that if max left of x, so everything is this part is similar to the linear search and this part is similar to the linear search as well. The only actually this one is also similar. This is 3.1, so this is 3.2 is not similar, so we're going to look for this one, okay? That is, if max left of x is greater than min right of y. This should not be the case because max left of x has to be smaller than or equal to min right of y. And if this condition is not satisfied, then we say that the x values which we are looking for is way larger than we want, right? We don't want these larger values, man. We have to move our high pointer to the partition of x minus 1. It's like the partition was on this side, the px was pointing on this element. Now it's a very big element, so we are going to move our low and high pointer to this one so that we can search on the smaller elements of x, smaller x values. That is why we change our high value to partition x minus 1. And I think if you have a basic knowledge of binary search, then you can understand how and why we have to move our high and low pointer and how do we do that. So if our x values are way smaller than the y values, and we want bigger values, we want larger values of x, so we're going to move our low pointer to px plus 1. And this problem has a so first of all, the space complexity is similar, right? The space complexity is similar, that is constant, because we are not using any uh, auxiliary vector or array to store the merged array or anything like that. And the time complexity, okay, so this one is interesting. So we are applying binary search on the minimum element, right? Which means the log of not m but actually minimum of n comma m. Yeah, so this is our binary search, which is even better than what was asked from us in the question. The question says that can you do it in log of m plus n, and we have even optimized it and used, because log of m plus n is actually dominant term and order of log of or minimum of n comma m is like an is a little bit better term than this one. So this is our four approaches, and I hope that you have some idea how we come up with this solution. So if you think that you still have some doubts, then I will say that go to the manually debug this part, because I have done the same. Manually debug your partition points and check your partition point, dry run your code for the simple examples like 4 5 elements, and try to debug these items as well, these values as well, that what is the max left x value, max left y value, min right x, min right values. And if you can understand these two parts only, if you can understand these two parts, then this condition is very much intuitive. You can easily grasp this condition. And if you are confused with this part, then I will say that you should try to revise the concepts of binary search. Okay, and then you'll be good to go. So I hope I was able to help you with this question. And if you think that there is still some improvement I should have done or should have approached problem in a different manner, then do let me know. And thanks for watching, guys. Bye.